2.7, we're dealing with inverse functions. We're going to find inverse functions informally and verbally, and verify that two functions are inverse. Look at the graphs of two inverse functions. And by looking at the graph, can we determine if they're inverse or not? And the answer to that is yes, we can. We're going to talk about a horizontal line test. I think we've done these before, haven't we? Last semester. So we're going to talk about a vertical line test. We've talked about that a lot in the past, haven't we? But now we're going to talk about a horizontal line test. Okay. And then find the inverses using algebra. So lots to cover today. We know that a set of ordered pairs can represent a function. For instance, f of x equals x plus 4, that's a function. If I have a set domain and I call that set A, and let's say those numbers are 1, 2, 3, and 4, I can plug each of those numbers into the function f of x, and it's going to give me a set B, right? So if I plug a 1 in, 1 plus 4 is 5. If I plug a 2 in, I get 6. Plug a 3 in, I get 7. Plug a 4 in, I get 8. So f of x being x plus 4, using the domain of 1, 2, 3, 4, gives me the range 5, 6, 7, 8. In this case, by interchanging the first and second coordinates of each of these ordered pairs, you can form the inverse function. So to find the inverse, you swap x and y. Remember doing this in the past? To find the inverse of a function, you swap x and y. That's all there is to it. Swap x and y. Okay. So the inverse of x, which was x plus 4, and it's not always going to be this simple, but the inverse of that is x minus 4, which should be simply swapping. So instead of the 0.15, I now have the 0.51. Instead of 2.6, I have 6.2. Instead of 3.7, I have 7.3. Instead of 4.8, I now have 8.4. So all I did was I swapped the x and the y's, and that is the inverse. The domain of f is equal to the range of the inverse. Well, does that make sense? If a function and its inverse, you swap x and y, right? Well, if you're swapping x and y, doesn't that mean the domain and range swap too? Because the domain was the x, but it's now the y, so it's now the range. Okay? When you form the composition of f with f inverse, or the composition of f inverse with f, you will get the identity. And here it is worked out. I'm going to go ahead and work it out again step by step. Our f function, f of x, was x plus 4, right? And our f inverse of x was x minus 4. So if I do the composition of that, if I take f of f inverse of x, means I'm going to take the f function, and everywhere I have an x, I'm going to put some parentheses there. So here's my f function. My f function is x plus 4. But what am I changing the x to? The x is changing to the inverse, which happens to be x minus 4. So I'll plug that in there. Well, in this case, the parentheses can be just dropped, right? And then I have x minus 4 plus 4. What is x minus 4 plus 4? Okay. And that's what they did. I'm just kind of talking through it. That might be helpful for you. So if you take the inverse and plug it into the original function, you're going to get x. Do it the other way around, you're going to get x. Always. Okay? So if I give you two functions and I ask you, are these two functions inverses of one another? What do? You plug them into each other. If you get x both times, you have to get x both ways. If this is true, then yes, they are inverses. Questions on that? Okay. I did not write and walk through the other one, but it follows the same methods. Finding the inverse of a function. To find the inverse of f of x equals 4x, This is what we're going to do. We're going to find the inverse and then verify that this is true. So to find the inverse, I start with f of x equals 4x. What's another way of saying f of x? Y. Okay. So if I change this to y equals 4x, they don't really go through the process here of how you go about finding an inverse. To find the inverse, you will swap the x and the y. So I'm going to go ahead and change colors now because this is going to be a different function. So this was y. It's now going to be x equals 4. This was y. It's now, this was x. It's now y. Okay. So to find the inverse, step number 1, swap the x and the y. Step number 2, solve for the new y. How do I get this y by itself? Okay, if I divide both sides by 4, I get y equals 1/4 x, or I could write that as x over 4. Yes? You swap all of them. All of the x's become y's, all the y's become x's. So if you have an x squared, it's now y squared. Okay? All right. Now, I can't say that y is equal to x over 4 because y is 4 over x. So now I need to give this y a new name. That makes sense? I'm not going to call it, I can't say y is x over 4 when y is 4 over x, when y is 4x. So instead of changing this to y, I'm now going to call this f inverse of x, and that is x over 4. Okay, so that's the steps that they went through to finding that inverse. So that was step number 1, find the inverse. Now, let's verify this. It's possible that doing this math, though it was only one step, we screwed up. Well, to find out if this is true or not, we need to find the composition of these functions and see if I get x both ways.
So if it's the inverse, why would inverse of x not be negative?
I didn't say it was the opposite. It's an inverse. Okay, so to verify this is true, I want to know, is f of f inverse of x, is that going to be x? Well, let's figure it out. I'm taking the f function. My f function is 4x. So here's my 4, but in place of x, I'm going to put f inverse, which is x over 4. What happens when you take 4 times x over 4? The 4's cancel, leaving you with x. So going from this direction, does it look like our math is right? Does it look like it's an inverse? Yes, but you can't just check one. You have to check it both ways. Okay. So I also want to know, is f inverse of f of x? Which means now I'm going to take the inverse function, which is x over 4. So in my numerator, my x is going to be 4x divided by 4. What does that equal? X. So it didn't matter which way I went. If I plug the function into the inverse, or if I plug the inverse into the function, I got x both times. So is our math right? Are these inverses? Yes. Okay. Questions on that? And here they did it, the same thing I just did. Moving on. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. Under these conditions, the functions g is the inverse function of the function f. and we denote that by saying f to the minus 1. That is not an exponent, okay? If you see an f and it looks like an exponent of minus 1, that means the inverse. So f of f inverse of x is x, and f inverse of f of x is x. The domain of f must be equal to the range of the inverse, and the range of f must be equal to the domain of the inverse. So again, all x's and y's swap. The domains in the range swap. Questions so far? I just talked about this. Don't be confused by the use of -1 to denote the inverse function. In this section, whenever f inverse is written, it always refers to the inverse of a function and not the reciprocal. They're not the same. I'm just going to move on from this slide. Okay. If you were to graph a function and its inverse, they will be mirror image. They are reflected across the line y equals x. That's why when you plug one into the other, you get x. So this function here, the black one, and the light colored graph, do those appear to be symmetrical about the line y equals x? Yes, that makes them inverses. We just did f of x equals 4x, and we did the inverse was x over 4, right? So if I go to y equals, if I do 4x and x over 4, we said that those were inverses, right? And I'm going to zoom square to make it look better. Do those lines appear to be symmetrical about the line y equals x? Okay. And I'll go ahead and come down here and put the line y equals x in there for you. Okay. So it is symmetrical. Any questions on that? Okay. Sketch the graphs of the inverse functions 2x minus 3 and 1/2 of x plus 3 on the same rectangular coordinate system to show the graphs are reflections of each other on the line y equals x. All right. F of x, 2x minus 3. 2x minus 3. The inverse function, 1/2 of x plus 3. And I'm going to go ahead and leave that dotted line for y equals x. Did I type it right? Everything look good? Okay. What do you think? Do they appear to be inverses? Okay, so graphically, we did this by looking at the graphs. That's what it means by graphically. Okay. We can also do this algebraically. Yes, I can. Yeah. And I was lazy. Instead of typing 1/2, I typed 0.5. And y3 is not required. I think it makes things a little easier to see if you put it in there, but if you don't, you're okay. You don't have to. So there it is. You can check points. That's another thing we can do is go back to the calculator. Look at the table. It's harder to see here. 813 is the point. Oh, geez. Table set. Change it to auto counting by ones. Okay. Notice how on one function we have 1, -1. I bet if I go up to -1, this value is going to change to a +1. Because these values switch. You see that? So this was X, this was Y. Swap them. Okay. And you can see that on throughout all the points on the graph there. Moving on. This is what I just talked about. If you were to compare points, you will see that the X's and the Y's swap. The reflective property of the graphs of inverse functions gives you a nice geometric test for determining whether a function has an inverse function. This test is called the horizontal line test for inverse functions. A function f has an inverse if and only if no horizontal line intersects the graph at more than one point. Can a parabola have an inverse? If I was to draw a parabola, any parabola, can I make an inverse to that?
Yes.
No, I cannot. It fails. It fails the horizontal line test. Do what? We're reflecting across the line y equals x. Okay, think about it. If I was to reflect this across the line y equals x, it's going to look like, and this is not going to be a very good reflection. It's going to look something like that, maybe. Is this a function? That's why there's no inverse, right? If it fails the horizontal line test, if you reflected it across line y equals x, it's not going to be a function. Okay, the only way you can have a inverse is if you can pass both the vertical and the horizontal line test. Okay. If no horizontal line intersects the graph, did I get everything on that slide or did I skip a half? I did everything. Okay. If no horizontal line intersects the graph at x more than one point, then no y value is matched with more than one x value. This is the essential characteristic of what's called one-to-one functions. If a graph passes a vertical line test and a horizontal line test, is a one-to-one function. That's an important vocabulary concept that you'll probably see. One-to-one must pass vertical and horizontal line tests. A function is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. A function f has an inverse function if and only if the function is one-to-one. I could take a parabola and restrict the domain to make it have an inverse. For instance, f of x equals x squared. That's the parent parabola, right? You know what that looks like. If I said f of x equals x squared, but x is greater than or equal to 0. Do you see what I just did? By establishing that domain. To graph this guy, here it is. Right? Because I ignored the other values. Now, is this function one-to-one with my restricted domain? Does it pass the horizontal line test? Does it pass the vertical line test? Yes. So by restricting the domain on this function to x is greater than or equal to 0, this function is now one-to-one. That makes sense. Can I have an inverse of this guy? Yeah. The inverse is going to look like this. F inverse of x is equal to the square root of x. Okay. Questions on that? Okay. Here's x squared. The table on the left is the table of x squared. The table on the right is the same table, but with the values in the columns interchanged. Is this 1-to-1?
Yes, no.
Got a problem, don't we? Okay. Okay. So I can take a function and I can swap x and y, right? Does that make them inverses? Not necessarily, because this is clearly not one. The table on the right does not represent a function because the point x equals 4 is matched with two different values, -2 and 2. So f of x equals x squared is not 1-to-1 and does not have an inverse. And I've said this many times today, haven't I, already? Okay. So f of x equals x squared is not 1-to-1 unless we do what? Restrict the domain. Okay, if I can restrict the domain, I can make it happen. Here's the graph of x cubed minus 1. Does it pass the vertical line test? Yes. Does it pass horizontal line test? Yes. Can I find an inverse? Yes. Okay.
Horizontal line test go all the way down to. Go horizontal. Well, I'm saying this would technically win because it flips on the other side.
It's still horizontal. This line, this graph goes down forever on this side and up forever over here. Okay, so it's always going to touch it once, right? Going up, it's always going to touch it once. Okay. No horizontal line intersects the graph of f more than one point. You can conclude that f is 1-to-1, and because it's 1-to-1, does it have an inverse? Yes. If and only if. Do y'all remember how to abbreviate if and only if?
If with
Two F's. Okay. If and only if means you can read it forwards and backwards, and it's going to be a true statement. Okay. It's cloudy outside if it's raining. Typically true, right? It's cloudy outside if it's raining. Most of the time you don't walk outside in the sun and have rain, right? So it's cloudy outside if it's raining. Can I reverse that? It's raining outside if it's cloudy? Not necessarily, right? So that would be an example of a not an if and only if, because it can be cloudy and no rain.
Did you look outside and see that?
No. No.
What if there was rain?
That's called the fox rain. It's not a big deal. It's usually that's usually a really light rain. Yeah. The graph of the function given by x squared minus 1 is shown below. It is possible, because it is possible to find a horizontal line that intersects the graph more than one point, you can conclude that this graph is not 1-to-1, and because this graph is not 1-to-1, it does not have an inverse. X to the fourth, anything that's like an up or a down is going to fail, right? Do what? No. Do what? Yeah, it's going to fail. Okay, moving on. Finding the inverse algebraically. For relatively simple functions, you can find an inverse function by inspection. For more complicated functions, it's best to follow these guidelines. The key step in the guidelines is step 3, swapping your x and y. The step corresponds to the fact that inverse functions have ordered pairs with the coordinates reversed. Here are the steps to finding an inverse. First of all, make sure there is an inverse. Does it pass the horizontal line test? If it does not pass the horizontal line test, stop here, right? Don't swap your x and y. You're going to do a lot of unnecessary work. Step number 2, in the equation for f of x, replace f of x with y. That's what we did a while ago. Step number 3, swap x and y. Step number 4, They say to go ahead and replace the y with f inverse right now. I don't do that. I leave it y. If you'll notice, I changed colors, right? My original equation was blue. When I swapped x and y, I went to red. And I left it in red. And at the very end, then I changed the y back to f inverse. Because if you have multiple y's, writing f inverse a bunch of times can get very sloppy. So I don't necessarily do step 4. Step number 5, make sure it's true by doing composition of functions. Plug f inverse into f, plug f into f inverse, make sure you get x both ways. That step is very important. So find the inverse of 5 minus 3x divided by 2. They've graphed it for us. Does it pass horizontal line test? Is the function 1-to-1? Yes, it passes both vertical and horizontal, therefore it is 1-to-1. Okay, let's find the inverse. F of x is my y. I'm going to swap x and y. So this becomes x equals 5 minus 3y divided by 2. Let's get y by itself. What would you like to do? Multiply both sides by 2. 2x equals 5 minus 3y. Next step. Subtract 5. 2x minus 5 equals negative 3y. Divide both sides by negative 3. So 2x minus 5 over negative 3 equals y. Is that good? Is that true? Okay. I would probably write it as negative 2x plus 5 over 3. Because I don't like having a negative sign, a negative number in the denominator. Okay. So how did I do that? I multiplied the top and the bottom by negative 1. Is that legal? Multiplying a fraction by negative 1 over negative 1? Because negative 1 over negative 1 is 1. Okay. So that's the step to solve to see if it's true. Now we need to find out, are we right? Is this really the inverse? I don't know. I've quit trying to guess what Cengage is going to do. Okay, so that's how you write the inverse. Now, to find out if this is true, we would want to actually work out f of f inverse of x and see if we get x. We'd actually want to take f inverse of f of x and see if we get x. Okay. And that's just more of section 2.6 about calculating inverses. I don't want to spend any time doing that. It's probably done in the notes as we move forward. Y'all good with this? Okay. They swapped x and y. They multiplied by, they did different math. Oops, let me go back. Do what? This is a different problem, isn't it? Yeah, this is it a different problem or same problem?
It's the same problem.
Same problem?
Actually, no. No. They did something different. Yeah. They added. They somehow made it x minus 1. They did y times 3x plus 1.
multiplied by 3.
I'm trying to follow their logic here.
I'm looking at that too, and it. Where did he get 3, 1, 2?
Okay. I'm just moving on. Okay. And folks, that is it for 2.7.